Today, we'll take a look at an interesting MySQL deadlock that I recently discovered in our codebase. So, some high-level descriptions first. So, what is a SQL deadlock? So, deadlock occurs when two or more SQL transactions, so we got two transactions, are waiting for each other to release a lock. So, one transaction grabs a resource, and the other transaction grabs a resource, and then both of these are waiting for each other to release the resources they grab, hence a deadlock. So this deadlock that I recently discovered has to do with the way that we're doing upserts. So an upserts combines the words update and inserts. So it's data operations that inserts a new row into a table if the row doesn't exist, or updates the row if the row does exist. So let's look at the actual code. So here's the way that the problematic pattern was doing it. So this is inside the transactions. First, it tries to do an update where the ID is unique, where the ID is the primary key. It tries to do an update. And if the update statement does not affect any rows, so like the row count is 0, then it doesn't insert. So this is done for performance reasons, because most of the time we expect that an update will be done, maybe like 99% of the time we expect the update to be done. And an update is faster than an insert. So we do an update, and then if the update doesn't work because that ID doesn't exist, then we insert. This is another way to do the same thing. We do insert on duplicate key update. So this is a single statement. And it's kind of the opposite of that. First, it tries to do an insert. If the insert fails, then it doesn't update. But in this case, we were optimizing for updates. So what is the problem here? So let's jump into an actual example that demonstrates this problem. Just for reference, our transaction isolation is the default, so that's repeatable read. I'm not going to go into details about transaction isolations, but changing the isolation level is a way to reduce, eliminate, or modify how deadlocks happen. So let's go into an example. So we're going to create this table. It just has an ID, which is a primary key, and an amount, which is another unsigned integer. So we're going to create this table. Create the table. We'll insert one row into that table. So we can look at this table now. Select stuff from my table. This table has a single row. Next, we're going to start a transaction. Start a transaction. And we're going to do an update here. We're going to do an update on an ID that does not exist. Now, let's go to a different thread. And that thread will also start its own transaction and will also do an update, but on a different ID. So these two threads in parallel are effectively trying to insert a new value into this table, but they're using this update first, then insert pattern. So this one's going to do an update. And then let's say this one wanted to do an insert. So you see it's waiting. It's not doing insert because it's being blocked by this guy. So what happens if this guy now tries to do an insert? We hit a deadlock down here. We hit a deadlock. So let's roll back and look at some details. Roll back here, roll back here. So to look at the details, we're gonna use this show engine InnoDB status, and it should give us some details. So it's going to tell us the last detected deadlock. This transaction inserted into my table. It holds this lock. So what is this lock about? This is a supremum lock. And it is a next key lock, right, that occurs because we try to update a value with an ID that didn't exist. So this next key lock grabbed, basically locked every value that's higher than the current ID in the table. And the same thing happened for the other thread. So both of those threads grab this supremum lock. So we see one thread has it, and then the second one also has it. So both of the threads said that we cannot allow any new IDs to be added to this table. So that's why we have a deadlock. So let me demonstrate this a bit more with a diagram, right? So we got one process, it did the update which failed, which did not update any rows, but grabbed a lock. The other one did the same update, well, not the same update on a different ID, but it also grabbed the lock. And then both of these inserts could not proceed and resulted in a deadlock. Just for your reference, another way to debug deadlocks is to use this InnoDB print all deadlocks approach. So let's think about how can we eliminate or fix these deadlocks. Well, one way to fix these deadlocks, as I mentioned, is to use the insert into on duplicate key update. This reverses the update and insert, right? So this will not result in a deadlock. Another way is to do this update, but if the update fails, right, we check how many rows are updated. I think there's a command to do that. I think it's row count, select row count, something like that. I think I don't need the ads here, so let's run this. Yeah, this returns a 0 because nothing was updated. So if nothing was updated, we could roll back the transaction and then retry it again, but without the update, either use a naked insert or an insert on duplicate key update. Another thing we can do is not to use transactions. Perhaps there's a way to accomplish the same thing without transactions. Of course, that's not suitable for other cases. And of course, there's other ways to solve this, kind of depending on the application needs. All right, so in conclusion, this update insert pattern that we discuss could cause deadlocks if they're inside transactions and multiple transactions are trying to insert simultaneously. And to prevent deadlocks, we can use insert on duplicate key update pattern. We can roll back. We can not use transactions, or we can find some other solutions specific to what our application is actually doing. That's it for today.